Welcome back. Now I will discuss what is inverse fast Fourier transform using Radix-2 method. In the previous video, you've seen that I've converted this x of n into x of k using this Radix-2 method. So, and we also seen that if we reverse the bits, if this is 0 0 0 and this is 0 0 1, and if we reverse the bits, apply bit reversal, it will be decomposed into 2-point DFT. So now I want to apply inverse Fourier transform. The only difference in this method is just you will have to use W of n minus k. In the previous lecture or previous video, we were using W of k. In this, just 1 minus 1, this is 2 point. It doesn't have any effect. If we move from there, it will be same, and if we move from there, it will be same. Yes. So it will be 1 minus 1 1 minus 1 1 minus 1. That is W of 2 1 2 0 and 2 1. W of 2 0 and 2 0 and 2 minus 1. Similarly, just add, subtract. How I place these arrows according to the formula that I have derived in the previous lecture. X of k e of n plus w of n k of n. So according to this, I want to get the values, so I apply this formula over there. When we have 4-point DFT, we divide circle into 4 parts, 1 minus j minus 1 j. So in this case, I will write, I'll move counterclockwise in the circle and will have 1 j minus 1 minus j. The rest of things are same as we did in the IFFT. Just simple even 1 plus j, this is W and the odd one. It comes out to be 8. And if we further divide this into 8 parts, what will happen? This is W of 80, W of 81, W of 82, W of 83, W of 84, W of 85, W of 86, W of 87. Similarly, 85, 86, 87. Just this is W of 80, this is W of 8 minus 1, just replace by minus 1, which is 7. So I'm moving counterclockwise. This sign has been replaced by minus. So W of minus 2, W of minus 3, W of minus 4, W8 minus 5, W8 minus 6, W8 minus 7. The rest of things are same. How I draw these arrows according to the formula that I discussed again and again. So if we apply 2-point FFT, IFFT on this signal, we receive this pattern. The original signal that I started with in the previous lecture in time domain was like this one: 1 minus 1 2 0 1 minus 1 1 3. And in this case I have 8 minus 8 16 0 8 minus 1 8 24. So what's the relation between these two? Is the only thing: divide the all values by n, which is 8. So if we divide, we'll have x of n like 1 minus 1 2 0 1 minus 1 1 3. It is same as I started with, because in inverse DFT we have seen that 1 over n was there in the formula. Now if I have the sampling rate and I want to notch out the frequencies, what I will do? If I have Fs is equal to 20k, samples are 8. What is frequency resolution? Frequency resolution will be delta F is equal to Fs by n. We have seen this formula in the previous lectures. So 20k divided by 8 will be 2.5 k. The first frequency is at 0, 2.5 k, 5k. The second one in frequency domain, 7.5 k, 10k. So the maximum frequency would be at Fs. F max is equal to Fs is equal to 2F max, and if I want to find F max, it will be Fs by 2. So this will be the maximum frequency, and rest of them it will like conjugates. So if I want to apply the filter that is 4 kilohertz, and I want to eliminate the values or the frequencies that are less than 4 kilohertz, what I will have to do is just make these frequencies 0. It's conjugate also. So the signal in frequency domain will be like 0 0 minus 1 plus j5 minus 2.121 j 3.121 4 minus 1 1 point. So x of k will be like this. Now if you want to see how it will look like in time domain, just apply the inverse fast Fourier transform Radix-2 method or IDFT as you wish, and you will see these are low frequencies and are notched out and have high frequencies there. So if you have high frequencies, then the transitions will be high and amplitude difference will be greater. So that's it for today's lecture. In the next lecture we will see what is sampling theorem and how it is used in MATLAB also.